This is a presentation for ITCS 2025 on our work, Complexity Classification of Product State Problems for Local Hamiltonians. I'm Justin Yurka. My co-authors on this work are John Callagher, Otis Parek, Kevin Thompson, and Yipu Wang. I'll start with a brief review of some quantum computing background and notation. Hopefully it's a refresher for those who have seen this before. So an n-qubit quantum state is a unit vector in an exponentially large complex vector space. We tend to use this ket notation to denote column vectors describing states. Flipping the ket produces a row vector via the conjugate transpose. Measurements are inner products with certain operators A, which give a scalar, usually a probability. Tensor products are how we write states of multiple qubits next to each other, and the dimensions of the spaces multiply. So that's how we go from two-dimensional qubits, 2 times 2 times 2, you get an exponentially large vector space. And finally, in this presentation, we'll be using an alternative way of writing quantum states as mixed states, which are square matrices instead of vectors. In this work, we're interested in Hamiltonians, which are exponentially large Hermitian matrices. They encode the constraints or interactions between particles in a system. Their eigenvectors correspond to states of that system, and their eigenvalues, the energy of the system when in one of those states. Most often, we're interested in k-local Hamiltonians, which have concise classical descriptions. Here, the Hamiltonian can be written as a sum of small Hamiltonian terms, each acting on at most k qubits. In this way, Hamiltonians are the quantum version of constraint satisfaction problems. Just as in 3-SAT, here, each Hamiltonian term acts on at most k variables, but those constraints and interactions can be overlapping and lead to interesting behavior. The classic problem in quantum complexity theory is the KLH problem, which is given some k-local Hamiltonian to estimate its minimum eigenvalue, or its ground state energy. This is analogous to the classical max-SAT problem, in that it is asking how satisfiable is the system? How many of the clauses, terms, or constraints can we simultaneously satisfy? In particular, for the Hamiltonian, how many terms in the sum can we simultaneously achieve a small energy against? And in complexity theory, we're often interested in the complexity of problems restricted to specific inputs instead of considering all possible inputs. One example classically would be to take SAT and restrict the allowed clauses. So for example, if you consider max SAT, but the only type of clause or relation that's allowed is the not equal to relation, that produces instances of max cut. So quantumly, we define a Hamiltonian family by which k-qubit terms are allowed. We do not allow arbitrary k-qubit terms, but instead fix a set of allowed terms. And for any fixed set S of allowed terms, we define the SLH problem to be KLH with the promise that terms are only drawn from the set S, as well as allowing weights, and you can, of course, change which qubits each term acts on. And with this setup comes the idea of a complexity classification, trying to classify the complexity of the problem based on the set S. This goes back to Schaeffer's famous dichotomy theorem, which says that for any fixed set of Boolean clauses, SAT is either NP or it's NP complete, with no intermediate. In quantum complexity, we have this result from Cubitt and Montanaro with Baravi and Hastings that classifies the local Hamiltonian problem for any set of 2-qubit terms. They showed that the local Hamiltonian problem is either in P, it's NP complete, Stockholm complete, or QMA complete. And the properties that decide which case S falls into are efficiently checkable. So given any set of 2-qubit terms, their work can tell us which case the ground state problem would belong to. And finally, the final piece that we need to introduce to understand our work is product states. So a product state is an unentangled tensor product of single qubit states. These are intermediate between classical states and general quantum states because each qubit individually is allowed to be in superposition. The thing that we do not allow is entanglement across qubits. A nice property of product states is that while general quantum states require an exponentially long classical string to describe, product states can be described qubit by qubit, and so they have concise classical descriptions. We also know that product states are nearly optimal for many natural sets of Hamiltonians, that they well approximate these Hamiltonians ground states. And so they've become a popular ansatz or subset over which to optimize for Hamiltonian approximation algorithms. And from there, we can redefine KLH and SLH in terms of product states. So instead of optimizing to find the minimum energy over all states, we ask what is the minimum energy over all product states. And then the question naturally becomes, can we classify the complexity of this problem as a function of the set S of allowed terms? So that brings us to our main theorem. We show that for any fixed set of 2-qubit Hamiltonian terms, if every matrix in the set is one local, then the product state problem is in P. And otherwise, if S contains any non-trivial 2-qubit term, then the product state problem is NP complete. Combined with the previously mentioned results from Qubit and Montanaro, this has the nice corollary that for any fixed set of 2-qubit Hamiltonian terms, the general ground state problem is at least NP hard, whether that's NP complete, QMA complete, or Stockholm complete, if and only if the product state problem is NP complete. And similarly, the general ground state problem is in P, if and only if the product state problem is in P. And this suggests that the idea of using product states as a first step in approximating general ground states for hard instances of the ground state problem might need to be rethought, given that if the ground state problem is hard for some Hamiltonian family, then so too is the product state problem. Now I'll just give a brief outline and then we'll spend the rest of the time going into details. First, if every term is one local, then it's straightforward to argue that we can optimize the state of each qubit individually. That's because one local means that the interaction or the energy contributed by one qubit is totally independent of the energy and the state of the other qubits. So that places the problem in P. The product state problem is always contained in NP, using the concise classical description to verify the energy of that state. And so the thrust of our work is to show hardness, that given any non-trivial 2-qubit term, the product state problem is NP hard. So let's begin with an example. Instead of considering arbitrary terms, let's consider this particular Hamiltonian term, this XYZ interaction. Now recall that X, Y, and Z are the Pauli matrices. These form a basis of 2x2 Hermitian matrices. And we will write our quantum states in what's known as the block vector form. So instead of thinking of a column vector, we're going to use the 2x2 mixed state. And that mixed state is a Hermitian matrix so we can write it in the Pauli basis. So expanding the state of a qubit A in the Pauli basis, we get an expression that looks like this. And the block vector is that vector of coefficients. Then we can plug this into the calculation for our chosen term H, and the energy of the interaction between qubits A and B simplifies, many of the terms cancel out, and it turns out that the energy is exactly the inner product between the block vector A and the block vector B. So for this particular term, this XYZ term, the product state problem on some interaction graph where the term H is applied to various pairs of qubits, potentially with various weights, is equivalent to optimizing this sum of inner products. Now, for general Hamiltonian terms, instead of a specific example, when we expand in the Pauli basis, we end up with this sum, which includes additional coefficients. Then writing the states A and B in terms of block vectors and doing the calculations, we end up with this expression. So again, there are inner products, something similar to before, but there's these additional terms and additional coefficients. So the question is, can we show anything about this objective function? And in particular, we try to simplify this expression such that it will be easier to show that optimizing over it is hard. And that brings us to Hamiltonian gadgets. So we'll have two tricks. The first trick is to symmetrize. So in general, the orientation of a two-qubit term does matter. Applying it to AB is different from applying it to BA. And this is inconvenient, so what we choose to do is that anytime we wish to apply the interaction to a pair of qubits, we apply it in both directions. And so if we are able to show hardness using this symmetrized term, that of course will imply that the original term was sufficient for hardness. Our second trick is going to be to delete the one local terms. So that corresponds to these terms involving the coefficients C and W. To do this, we borrow a nice gadget from previous work that if we want to apply an interaction between U and V, we're going to introduce two ancilla or helper qubits A and B, have this gadget of interactions weighted with positive and negative weights. And it turns out that when all of these interactions are applied, the one local terms cancel each other out. And so what we're left with after these tricks 1 and 2 is that if we want to interact qubits U and V, we apply this gadget, and we get this expression that is a single term rather than many terms. And it has some similarity to what we saw with our example. There's clearly an inner product going on. Now, again, our intention is to interact qubits U and V. A and B are these ancilla qubits. They're effectively free. And so if we're trying to minimize the energy, they'll just take their optimal value. And so we end up with that the minimum value of this expression in terms of U and V is this. It is proportional to the distance between the block vectors U and V, stretched by this transformation matrix M, which depends on the Hamiltonian term. And so at this point, we have a path to connect the Hamiltonian problem to graph problems, or at least graph and vector problems. In particular, given some arbitrary graph, we can begin with any non-trivial Hamiltonian term and construct a large Hamiltonian using the gadgets that we introduced, such that we know that the minimum energy of a product state for that Hamiltonian is equivalent to this expression. And this final expression is can be given as just some problem in terms of a graph, no, without reference to a Hamiltonian. And so if we can prove that this problem in terms of graphs is NP-hard, that would prove that the product state problem on Hamiltonians is hard. And with that reduction, we now turn to graph and vector max cut problems. So recall that max cut is this classical problem in which, given a graph, we're asked to partition the vertices into two sets so as to maximize the number of edges which cross the partition. Alternatively, we assign labels trying to maximize the number of adjacent vertices with opposite labels. Now, there's a well-studied generalization called vector max cut, where instead of assigning plus and minus one labels, we now assign unit vectors to each vertex. And the intuition now is that instead of partitioning the vertices to the left and to the right, we embed the vertices onto a unit sphere, and we're trying to stretch the graph as much as possible. More precisely, the objective is in terms of the inner products, or the square of the distances of each adjacent pair. Now, the vector max cut problem does not exactly match the objective we found when analyzing Hamiltonians. And so we introduce a new problem, which we call stretched linear vector max cut. Here, given some weight matrix and a graph, the problem is to estimate this objective function, which is in terms of the stretched distance between vectors assigned to each vertex. And again, this objective function, matches what we were able to produce with our Hamiltonian gadgets. So here the intuition is now that given some graph, we embed the vertices onto the surface of an ellipsoid defined by the weights of the matrix W in order to maximize the sum of the distances between the points. And the theorem is that for any fixed non-negative non-zero W, this problem is NP complete. And this turns out to be sufficient for proving that our product state problem is NP complete. In particular, what we can show is that for any set S containing a non-trivial 2-qubit term, there is a corresponding weight matrix W such that stretched linear max cut with W is NP complete. And since we saw how to embed the value of stretched linear max cut into the optimal product state using the Hamiltonian term in S, this shows how we can reduce this NP-hard instance of stretched max cut into the Hamiltonian problem, implying that the Hamiltonian problem is in fact NP-hard. So how do we prove this result about vector max cut? We break into cases depending on the relationship between the weights, and we either use star gadgets or clique gadgets, which I'll briefly go into. Our first approach is to use star gadgets. So given some graph G, here, the graph formed by the blue edges, we construct a new graph by adding many ancilla vertices around the vertices of the original graph. Trivially, the ancilla vertices will all be assigned a vector, which is the negation of the vector assigned to their center vertex. This has the effect of contributing to the objective value in proportion to the length of the vectors assigned to the centers. So any deviation from the highest weight axis will be heavily amplified. In particular, if alpha is strictly larger than beta and gamma, then the only way for a vector assignment to achieve a large objective value is for all of the vectors to live along or near that one highest weight axis. This shows how the stretched vector max cut problem becomes an instance of the one-dimensional max cut problem. We also use clique gadgets. So in the case that alpha is not strictly larger than beta or gamma, we introduce a different type of gadget in multiple steps. So given a graph G, we construct a new graph by replacing each edge with a clique. In particular, or for example, you can consider a three-clique, a triangle. And we make a couple of observations. First, maximizing the total distance between the vectors assigned to a three-clique is equivalent to picking 3 points on an ellipsoid, which inscribe a triangle with maximum perimeter. Then we can use the fact that maximum perimeter inscribed triangles are somewhat unique. So in particular, consider that in a circle, once one point is fixed, there is a unique pair of points which form the maximum perimeter triangle with that one fixed point. Then we observe that once vectors are assigned to one gadget, that partially assigns vectors to any neighboring or connected gadgets. And we just saw that partial assignments of vectors fix the set of optimal vectors. And so vectors can maximally satisfy every clique if and only if a set of optimal vectors can color the entire graph. We need to be able to use the set of vectors we assign to the first clique on every clique. And this shows how to reduce three coloring to an instance of our vector max cut problem. Finally, I want to mention a result we show for quantum max cut. So for Hamiltonians in the unweighted quantum max cut model, we show that the product state problem is NP complete. This is distinguished from our main result because here we specifically show that in the unweighted model, the problem remains hard. We do not require using negative weights to construct a hard instance. This has a nice corollary of showing that this three-dimensional vector max cut problem, the original vector max cut problem we introduced, is NP complete, which is actually quite nice because it makes progress towards this conjecture of Lavache that vector max cut should be NP hard for any constant value of k. Finally, I'll conclude with a list of open problems and a summary of our work. Thank you for listening.